You ever watch a quarterback throw a perfect spiral or a kicker nail a last-second field goal and just think, wow, that's poetry in motion? Well, it turns out it's also calculus in motion. Seriously, today we're going to pull the math right off the blackboard and slap it onto the football field. Let's break down the hidden calculations that make a play not just good, but legendary.
I mean, really think about that for a second. To nail that kick, everything has to be perfect. The angle, the force, that's not just luck or guesswork, it's an optimization problem. And the tool that can actually solve that problem, whether the coaches know they're using it or not, is calculus.
You know, to really understand a football game, you can't just look at the final score. You've got to zoom in on those critical moments. The split second a quarterback releases the ball, or the instant a receiver makes a sharp cut. Football is all about instantaneous change. And that, right there, is exactly what calculus was designed to measure. Okay, so the main tool we use for this is called the derivative. Now, don't let the formula intimidate you. All it does is let us calculate the rate of change at one specific, infinitesimally small moment in time. It's the difference between a player's average speed over a 40-yard dash and their exact speed at the very instant they juke a defender. The derivative is like a freeze frame of change.
But what happens when a player's move is so sharp, so sudden, that it's almost impossible to measure? On a graph, we call that sharp point a cusp. And right at that point, the derivative is actually undefined. This is the perfect mathematical picture of a running back's signature move, a cut so abrupt that their direction changes in the blink of an eye. Mathematically, it's a moment of undefined change, but on the field, it's a total game changer. All right, so we can analyze a single moment. But how does that connect to an entire play unfolding down the field? Well, to really get the whole picture, we need to track a player's motion from start to finish. We need to open up their statistical playbook. It all starts with their position, right? We can call that S of t. It's just where a player is at any given time t. Now, if you take the first derivative of their position, you get their velocity. That's not just how fast they're going, but also which direction. And if you take the derivative of that, what we call the second derivative, you get their acceleration. It's like having a built-in speedometer and G-force meter tracking every player on the field.
Now here's a super important point. Velocity is not the same thing as speed. Velocity has direction. It can be negative, think of a running back getting pushed back for a loss, but their speed, which is just the absolute value of velocity, is always positive. They're still moving fast, just in the wrong direction. So speed tells you how fast, velocity tells you how fast and where. So when is a player actually speeding up? Well, it's a little more complicated than just having positive acceleration. A player's speed increases only when their velocity and their acceleration have the same sign. Think about it. They speed up when they're running forward and pushing forward. But they also speed up in the wrong direction if they're moving backward and something is pushing them backward even harder. They have to be accelerating in the same direction they're already headed. Okay, so we can track motion. That's cool, but how do we find the most important moments of a play? You know, the absolute top speed, the sharpest cut, the highest point of a pass. That's where we use calculus to find those highlight reel moments, what mathematicians call the maximums and minimums.
So let's ask a real practical football question. How do we find that one single moment where a receiver hits their absolute top speed, or the exact instant they plant their foot to cut and change direction? These are the turning points of a play, and calculus gives us the tools to pinpoint them exactly.
And the playbook for finding these moments is called the first derivative test. It's actually pretty straightforward. First, you find all the critical points. These are moments where the player's velocity is zero, like when they stop to change direction, or where it's undefined, like that sharp cut we talked about. Then, you just check what's happening on either side. If their velocity goes from positive to negative, boom, you found a local maximum, like hitting top speed right before they start to slow down.
This table really puts it all together. It shows how combining velocity, the first derivative, and acceleration, the second derivative, tells you the whole story. For instance, look at that top left box. Positive velocity and positive acceleration, that means the player is moving forward and hitting the gas. But compare that to the bottom left. They're still moving forward, but their acceleration is negative. That means they're hitting the brakes, maybe bracing for a tackle. Every single box here tells a different story about a player's motion.
Okay, this all leads us to the ultimate goal, optimization. We can use these tools not just to analyze what already happened, but to figure out the absolute best strategy for what to do next. This is literally how you calculate a win. At the end of the day, optimization is all about finding the absolute best possible outcome. For a quarterback, it might be finding the perfect launch angle to get the maximum possible passing distance. For a punter, it's finding the angle that gives you the maximum hang time, giving your coverage team that extra second they need to get downfield. It's all about finding the best. And believe it or not, there's a game plan for this, a 6-step process that works for pretty much any of these problems. You figure out what you want to maximize or minimize, you build a mathematical model for it, you use derivatives to find those critical points, and then, this is key, you prove that you've actually found the best possible solution. And this is where you see the real power, the real beauty of math. A textbook problem might ask you to find the most efficient shape for a soup can, but that exact same 6-step process can be used to find the perfect angle for a quarterback's pass to get maximum yardage. The context is totally different, but the mathematical strategy for finding the best is exactly the same. And here's a little pro tip for you, straight from the source material. Once you've found a critical point, a potential best answer, how do you know for sure that it's the maximum you're looking for? Well, the second derivative test is often the fastest way to check. It's the final confirmation that your game-winning calculation is, in fact, a winner.
So the next time you're watching a game, look for the calculus. It's there in the arc of a perfect punt, the pursuit angle of a linebacker trying to make a tackle, the explosive acceleration of a defensive end off the line of scrimmage. It really makes you wonder, what other parts of the game could you break down and optimize with just a little bit of math?